So the first talk, as I just said, will be given by Professor Yuval Elovici, who is the director of the Telecom Innovation Laboratories at Ben Gurion University of the Negev. He is head of the BGU Cybersecurity Research Group, research director of iTrust at Singapore University of Technology and Design, and also a professor in the Department of Information System Engineering at BGU. He'll be helped with this talk by Mr. David Berend, who is a PhD candidate at NTU Singapore, leading the National Standardization of Secure AI, Singaporean delegate to the International Standard Organization, and member of the German Standard Organization, TIA. They'll be talking about evaluating responsible AI for regulatory conformity.
And we are going to talk about the issue of how actually to guarantee that an AI system is mature enough to be deployed in a realistic environment. First of all, today we are developing many systems that are based on an AI component, where the AI component is a major component. For example, if you take my Tesla car, it's like you took an AI component and you built a car around it. And here comes the question, when we are developing a system that is based on AI, at what point we are confident that the system is mature enough to be thrown into the real world and to confront with inputs that are coming from the real world? That's a very big question. Now, why we are raising these questions? Because originally, in the machine learning lifecycle, when we are developing a new system, usually what we are doing, we are collecting a lot of data. Then we are processing this data. Then we are training and inducing a new model based on this data. And then once we induced the model, we are testing the model. And traditionally, when we are teaching also students, machine learning and AI, traditionally there are acceptable measures of performance, which is accuracy, precision, F1 score, false positive, true positive. There are many such measures of performance of an AI system that we are using. And usually we have a hunch what is the level of measure that is acceptable for the model to be ready. The question is, ready for what? Doing research is one issue, but when we deploy the system in a realistic environment, can the previous measures actually predict what will happen to the model when it's going to go and confront real data in the real world? We believe, we're trying to convince you later on, that the answer is no. The existing measures are not adequate to check whether a specific AI system is mature enough. Why? Because as you will see in the next few minutes, weird things happened to AI systems where they are deployed in the real world, where they are confronted with real data. First of all, what can happen? We divided the answer to the question of what can happen to 3 categories of failures. The first category of failures is a standard performance failure. For example, in this case, we see a Tesla car that drives in a specific road, and the road is known to the Tesla car, and still it fails to take the correct turn. Why? Because there was some small change in the environment that created a situation in which the AI algorithm failed to take the correct decision. This is something that is very close to the testing, and such failure maybe was supposed to be detected by the testing, but in some cases it's not detected by the regular testing that we did to the AI system before it was deployed. But when we are moving to the next level, what can happen? In this case, you see a Tesla car that made an accident with, in this case, it's a fire truck, or there are cases with ambulances. There are many cases that a Tesla autopilot didn't detect a police car. Probably the reason for all these crashes is because of an out-of-distribution failure. In other words, these cars or these situations were not represented well enough in the training set of the model. So when the model encountered these circumstances, it failed to take the correct behavior. But this is the second category of failure that may happen to an AI deployment in the real world. The third category, it's the most problematic, and you will see several videos that relate to that. Why it's the most problematic? Because in this case, somebody, adversary, knows that there is an AI system or a system using AI, and it tries to fool the system in a way that will give the attacker some kind of an advantage. As you will see, at least in this video, if you call phantom attacks, you will see that by using a simple projector that projects objects on trees and on the road, we can fool a Tesla car that includes the most advanced ADAS system that we know today. So let's see several examples how AI systems can be fooled in a systematic way by adversaries. This is the first example. In this case, we took Tesla, even Model X, which is the most advanced Tesla car, and we will show you how actually we can fool the car by using a new type of attack that we call phantom attacks. And you will see soon how in a realistic environment we can project something and the car believes that actually it's a real object. So in the first attack, what we are doing, going forward, yes, you see the car is driving, we are projecting Elon Musk picture on the road, and the car stops. And in a few seconds, you will be able to see how the AI system inside the car sees actually the scene, how it processes the scene. This is how the AI system inside the car sees it. It identifies the object, which is not 3D, just a projection on the road, and still it stops. So definitely, this implementation, which is the most advanced ADAS, is not mature enough to cope with attempts to fool it in a very, very naive way. Another example, here we are projecting lanes. We are projecting lanes, and it caused the car to drive to the left, especially if it's on autopilot. Again, we will show you how the AI system inside the car saw the environment. And as you can see, we could really easily fool the AI engine of Tesla. But what you saw before, in order to implement the attack, I had to be present in the scene. What we did later on is to do split of a second attacks on a digital billboard. You see a digital billboard presenting a stop sign for half a second, and presenting into a hack digital billboard a stop sign for half a second was enough to cause the car to stop. Again, you can see it in a Model X. We mimicked a digital billboard on the left, and we put in a split of a second a stop sign, and the car literally stopped. Now, such an attack I can do from remote because the attacker can hack into a digital billboard on the road and stop Tesla cars by adding a small split of a second stop sign to the advertisement on the digital billboard. or even a speed limit. The third demonstration of an attack against AI, what is special about this attack is that we used AI to do an attack against an AI algorithm. What we did here is actually we assume that we can hack into the communication between the CT scanner and the PAC server in the hospital, and using a GAN algorithm, we learned how to add tumors into a CT scan. You know, CT scan includes 500 layers, 500 images, and we managed to find an attack, how to use generative adversarial network to generate additional tumors that we added to the CT scan in a way that even definitely an AI algorithm, but even a radiologist couldn't distinguish between a real CT scan and a CT scan that was manipulated by us in order to create the attack. Soon you will see how actually we conducted the attack in a real hospital by using a simple Raspberry Pi that implemented the man in the middle, again, between the CT scan and the PAC server, with the permission of the head of the hospital. We entered to the hospital and installed this device. Nobody stopped us. Of course, it was with the permission of the hospital, but without the awareness of the security in the hospital. So you can see we can get into a hospital. Nobody stopped us. We found the location where to install the man in the middle between the CT scanner and the PAC server in the hospital. And after we did such an installation, we could manipulate every CT scan in a way that could fool an AI algorithm. By the way, today we have a Horizon project where our goal is to detect exactly such attacks by analyzing the CT scans and determining that actually the CT scan was manipulated by an adversary. It's like detecting deep fake in the domain of CT scans. So really, such an attack can be implemented very, very easily. And the goal is to develop technologies to identify before you are processing the data, that the data that you are processing was not manipulated by an adversary.
Thank you very much. I think together with the example videos, it becomes very clear that AI systems in fact have some flaws or like weaknesses which can be exploited that can't be measured by these traditional measures we have to evaluate whether a system should be deployed or not. And as more and more incidents occurred over the past, first regulations started to become aware about it. Most recently with the EU regulation draft that has been published in May this year. And there we've seen that now new principles arrived under the banner of responsible AI or trustworthy AI. And the focus here lies on not only the performance, but also the robustness against such attacks, for example. The security, how these attacks can infiltrate the AI system. The privacy, how the data that is used to create the system or which is processed is protected. And the fairness, where people are given equal fair opportunities, not related to any kind of humanitarian principles or personal sensitive features from themselves. So usually in these regulations, there are more or less precise determinations of what they mean, right? So when we look at the Data Protection Act, there we have a very clear way of this is the impact assessment on how you can evaluate how conform you are or not. But when we now take a look at the current drafts that are being developed, some things are missing. The terminology of what is robustness, what is meant by cybersecurity is vaguely touched. The assessment process is barely outlined, and no quality thresholds are defined, which may give us sense of what we can determine as good or high quality or low with low quality. And finally, the necessary governance around it, what institutions can provide such services, are also left out at the current place. So in essence, there are many new things or many new challenges that have to be tackled. So looking at what these regulations or regulators can do is always determined by the tools they have at hand. And as the tools become better, the more granular and precise regulations can be established. Looking at what we have right now, it seems that for the case for robustness, for example, three movements are taking place. One is the mutation generation to tackle the issue of data insufficiency. When new data points are created and sometimes correlated with the model behavior to find the nice spots where mutations should take place such that weaknesses or errors can be identified. Next level is the testing frameworks, which now harness these mutation generations and model behavior understandings to create test cases which can provide insights in how sufficient the testing is, how diverse it is, to give a more confident perspective of how much has been tested. And then, of course, the final test cases then provide the reporting foundation on which people can assume whether or not the system is good. But again, as these tools are still in their early stages, it's hard to quantify what is the exact point at which good can be determined. So what is required, looking at this regulation enablement, we have three stages which we can align along the AI lifecycle. Starting with the testing data selection, going over to the actual testing, and finally the reporting, which has to become more and more guiding on actionable statements rather than vague outlines. So if we walk through these individual steps, we can quickly see that whatever we want to do regarding the testing requires a very clear analysis of the testing data that we want to utilize. As AI systems are mostly data-driven, their logic is defined by the data that is used for them to learn. So whatever data we now use for testing is representative of the scenarios we want to test. So in traditional software, that would be called unit test, where we want to go through different code segments. With machine learning or deep learning, we now look in the unit test of data, where we want to cover certain scenarios. But we need to understand whether we want to go into a manual approach of assessing an AI system, declaring certain scenarios from the start manually, or having a more systematic approach, using, for example, clustering algorithms to determine the distribution of the data and thereby selecting the necessary test cases in the necessary sufficiency, diversity, and balance among them. So once we have defined those scenarios, those unit tests of data which we want to test or assess, now comes the how. What different testing strategies we use. So building on the motivation which Professor Elovici outlined, we can see that there are three levels of failure he presented. The first one was regarding the corner, where a car tried to go around a corner in a known environment, where small changes may trigger the system to fail, which hasn't been detected yet. So changing the brightness, changing the contrast, maybe rotating a little bit, enables the exploration of those existing data points in these more diverse settings that can be easily created, tested, and ensured that the AI system works in the most cases of that. And the second level is on the OOD mutation, referring to the ambulances or the fire trucks, where we now want to use more advanced mutations, for example, changing the weather, making semantic changes to the image, where we can help generating new semantic images into the data pool for assessment. And the final mutation category, which we here call level 3, correlates to the third level of failure, which was the adversarial attack, either related to the projection, understanding the image changes which you need to apply based on the makeup, and thereby looking at the system from the adversarial perspective and understanding how robust it is against such changes. And in all of this, the neural behavior understanding enables the insight in the completeness of the testing and the guidance what the next test should be. So summing this all up, looking at how many tests went well and how many tests went not well, we can create areas of confidence, areas of robustness, and limitations which can guide us in the way we should deploy the system. For that, we'll now go through each step on an exemplary base of the biometric case, and thereby more understand closer what it actually means. So looking back to the first start, at the data collection or analysis of our test set, we want to understand if the data we now have for the testing is representative of the different scenarios we want to cover. So if, for example, we have this face recognition allowing entry to a certain establishment or not, then we need to make sure that the diversity of our test cases is sufficient. And for this, for example, using systematic approaches, we can see what kind of skin types correlating to gender or ethnicity are so far covered and which types were left out, which better should be integrated, as it would then incur the final result from our testing report. Moving over to the next step, we have now the 3 levels of testing outlined to the right. So the first one would be we take existing pictures, existing testing sets, and then apply these standard mutations by enhancing the brightness, changing the contrast, or adding a bit of rotation there. The second level would be the out of distribution mutation, where we now change the age, change the expression, let them smile, let them show some teeth, or add eyeglasses. Note that all of these are generated images. And the final one is adding adversarial mutations, where we change some pixels or we apply specific masks in a similar fashion. Note that these pictures look all the same. The reason is they are in fact close to the distribution and are therefore difficult to identifying as outliers. However, these small changes which are not visible to the human eye make an extreme impact on the AI system, as we have seen before. And as we change pixels slightly, having a sufficient amount of changed pixels helps us in fooling the system eventually. So here, the things we should look out for is how many pixels does it need to be changed to cause a misprediction or a targeted one? And how much of change does these areas of the image need to incur for the prediction to change? And finally, to give a more practical example of neural behavior would be to see what the testing inputs are, measure what the neural network responds or how it is behaving to its input by the neural activation, and aggregating that to actionable guidance of the testing, meaning that blonde hair, for example, has not been tested sufficiently, and therefore new test sets or test samples should be generated of that kind. So finally, once this all has been assessed, we can aggregate the information into actionable guidance. For example, when we look at the level 1 testing, changing the brightness darker and darker can emulate the setting of night. Suddenly we realize that at some point of darkness, the system starts to fail significantly and the accuracy drops below the point where our application should perform much better. Hence, we can give guidance that the system should provide an alternative from 7 p.m. onwards, as the accuracy is too low at this given brightness level. Furthermore, we can say we now look at the level 2 testing if we start aging the test samples and identify that at some point of age, the accuracy drops significantly as well. Identifying that for elderly people, maybe they should not engage with the AI system in place and an alternative should be provided, providing better service at the given level of quality, which is communicated to customers. So these are the let's say testing areas where we can be confident given the necessary accuracy we have perceived. When the accuracy drops a little more, or let's say the mutations have been diverse enough, plus the general error rate we have perceived is less than in the area of confidence, but high enough for the system to still be all right, given the thresholds by the defined application, we can define an area of robustness, where we know that the system is able to generalize in some aspects, while some limitations may be encountered. For example, when it starts raining, light rain is still all right for the system. However, as soon as strong rain starts, the accuracy drops too much. So we can give guidance on a rain protection should be given outside of the AI system in case it is deployed outside. Or referring back to the makeup attack we've shown previously, given the adversarial attacks, how many pixels does it have taken to be changed, and at what level had they be changed in order to fool the system? Maybe it's better to add a guard as well, who checks if there had been extreme cases like the image we've seen here. So in all of this, we've now have actionable approaches which can guide the deployment and which can provide actionable ways to measure the robustness and to provide a confidence statement how to deploy it. And the key to this lies in the sufficiency of the testing, meaning that enough data points has been produced to enable a statistically correct view on the quality. A diverse setting, meaning that these test points cover the majority of scenarios or inputs the AI system will encounter once deployed, together with the test case selection strategy that enables this diversity in the first place. And then most importantly, such that the results are not biased towards one certain cluster that has been identified, having a relative to the amount equal testing of scenarios by selecting the test cases appropriately, and thereby enabling the completeness from a data-driven point of understanding, but also integrating a model behavior understanding. This can be the aggregation of neural activation, starting from the ranges that have been defined from the training data, how much each neuron is activated, looking into new test points which activate new areas of the neuron, which can then be aggregated for all neurons or for specific layers, and thereby understanding the coverage, also referred to as the testing adequacy, on how much now overall the new test cases compared to the training data stimulate the new behaviors of the model, and thereby enable the model perspective of completeness plus the data perspective of completeness, which together can form the perspective on quantifying the quality of trustworthy AI, for example, here in the robustness case. Looking at the testing in particular, we have the standard performance enhancement, which we've now seen, the OOD performance enhancement, and the adversarial performance enhancement, which are the next steps when we have the testing completed and we now move on to creating a better system that again then undergoes the testing cycle to understand if an improvement has been achieved. again, we can then quantify the quality and see if we are now at this point where we feel really confident in deploying the car. At this point, we have now established a good outline of what regulations need, where we stand from the tools, and what further research directions we should follow. And I'd be happy to give it back to Yuval for final notes for guiding these regulations.
Just a few insights that we thought together, me and David, about the final notes that we want to give is, first of all, it's very important that whatever tools we are going to develop, they are going to be accessible to everybody and they are going to be open source. It's extremely important that the tools and the data sets will be accessible and practical also to SMEs. We don't want to see a situation in which only huge companies will be able to certify their AI, because then what will happen is that all the AI suppliers are going to be only huge companies like Google, Apple, Amazon, and so on. So we want to have tools that are simple enough to be used also by small companies like SMEs. Also, what is very, very important, which is raised, it's a huge concern of me and David. I just give you an analogy. Let's assume that we have a specific testing solutions that test whether an ADAS complies with the regulation. What may happen is that companies are going to take these tools, they are going to develop an ADAS, advanced driving system, that is compliance with these regulations, and they're not going to focus on improving the system at all because they're complying with the regulations. So what we believe that we should embed in any one of these tools, it's a certain threshold that continuously needs to be increased. In other words, we are going to allow a certain level of robustness and in 2021, but in 2022, our demand for robustness is going to increase slightly. So this is going to motivate the companies to continuously improve the performance and the robustness of their AI solutions. We believe that this is very, very important in order not to create a stagnation in the evolvement of the quality of AI solutions.
Very good. Thank you, Yuval. We have a question from Giora Benedek, referring to the hospital example. The CT data was under TLS. The question is, how did you overcome it?
First of all, in reality, at least what we tested, there is no TLS used, no encryption used between the CT scanner and the PAC server in the hospital, because many hospitals believe that their environment is so secured that there is no need. Secondly, even if we didn't do the interception man in the middle, an attacker can hack the PAC server in the hospital and implement on the stored CT scans the same attack. And what we are focusing today in a research that we are doing in a huge EU project is how to identify what we call deep fake in CT scan and MRIs. How to identify that somebody manipulated the object in order to create some kind of a damage.
Thanks, Yuval and David, for this wonderful talk. I would actually encourage the audience to take this opportunity to ask as many questions as they want. In the meantime, I think I will bombard you with a couple of questions. So actually, it is again related to this CT scan example. And it is a problem of processing and encrypting and authenticating real-time data. And of course, there are solutions which exist which can actually solve it. But do you think, does the real-time put too much constraint to use those solutions, or like the existing cryptography might not be sufficient to address these?
Maybe we didn't convey the message good enough. we demonstrated the attack in real time, but the real risk is not in real time, because in radiology, when you are doing a CT, you are doing a CT scan, it is being stored in the PAC server, and sometime later, it could be 1 day later, half a day later, come a radiologist and inspect your scan and give a judgment. It is usually not done in real time. In this period of time where the data is stored in the PAC server, it's a server. Somebody can manipulate your CT scan. So, and the only solution is to prevent hacking or accessing to the PAC server, but it's a server like any server. I can tell you as an expert, I can attack everything. But in this case, the consequence is severe. Now, we managed to show that in our preliminary research, that when you are changing an image, you are not complying with physical properties of the machine. So actually, we are developing an AI algorithm that identifies the unnatural manipulation of the CT scan using AI.
All right. Thanks, Yuval. Also, I was wondering, there was, so we were talking in the compliance part, we were talking about a distribution-based approach towards detecting like all these attacks. But often, like a motivated attacker, especially for a targeted case, would like to play within the distribution. So in that case, like, are there any other approaches which could be helpful in this case? And another, like, to just continue with the question, like, do you think there could be a role of hardware here, where like we could actually improve the overall situation?
Should I take the first one and you the second?
Yes, okay.
Good. I think regarding the distribution, there are data-driven approaches where the attack is trying to move itself towards the distribution of the existing data and thereby result in a trigger to the model that then misclassifies it. And the detection of such comes from this data comparison, for example, using autoencoders that try to understand the error that has been involved. On the other hand, one thing that is interesting are either direct out-of-distribution techniques that use the model behavior directly as indicator if this data point has been fooled, where we can look at the penultimate layer, which provides the highest insight of model behavior, and thereby can aggregate it to higher or lower dimensional scores, which determine how far or close the input is to the trained distribution from the model perspective, or even train a separate model that perceives the data related to the in-distribution and thereby have a more granular perspective on what can be considered in and out of distribution, depending on what the attacker tried to push its initial attack towards. So if we test it from these two perspectives, the likelihood increases significantly to detect which of those are actually adversarial and which are not. Yuval, would you like to add something on that?
Yes, Kokons. I wanted to focus on the hardware. I saw a recent paper where they claimed that an adversarial sample consumes more energy in processing it than a non-adversarial sample. So such a solution definitely can be embedded in hardware because it's relatively easy to measure, you know, how much power consumption the AI algorithm did for a specific input, and based on that conclude that probably it's trying to fool the AI algorithm and implement it in a simple hardware. Otherwise, you know, it's trying to make the algorithm more robust. And the challenge is that today, attackers, especially once they know what is the defense mechanism that you are applying, they can always find an adversarial sample that can evade it. Now, this is true for the digital domain. When you are moving to the real life domain, it's a little bit harder, and it makes our life a little bit easier, because it's very, very difficult to implement an attack in the real world. But in the digital domain, at least until now, it was demonstrated that whenever the attacker knows what defense mechanism you are applying, he will be able to find at least one adversarial sample that can bypass it. And that's a very, very big challenge for us.
Yeah, like this goes in line with basically an attacker needs to be lucky once.
Yes.
Thank you, Yuval. We have another question from Seetal here, who says that regarding the fooling the car using adversarial images, may I ask if you have considered the input detection schemes like feature freezing?
We checked feature freezing, but it didn't help. What really helped, by the way, is to try to learn the context. We presented the attack, but eventually the solution that we proposed for the scientific community was to not only to look for a specific object in the scene, but also to look at the context. Now, once you're looking at the context, you can see, for example, there is a traffic sign, but it's on top of a tree. It doesn't make sense. So the context is a tree. Or for example, there is a stop sign inside a digital billboard. It's so simple. So this is at least was our defense mechanism, to try to understand, because it was not an adversarial attack. It was a phantom attack. It's not to understand the context in which the object is presented to the car, and by that, to tell him to ignore it. The biggest challenge is that for a car to ignore a detection, it's it's very, very hard for a car manufacturer to accept such a measure. Because if an accident will happen, you will prefer to be fooled than to ignore a real traffic light, a traffic sign.
Sure. All right. We also have another question from Shivam, who would like to ask, when you provide the test mechanism for type 3 failure, aren't you also providing the adversary the direction to change to fool the AI?
The answer is yes. As I said before, as far as I know, there is no full bulletproof defense mechanism for adversarial attacks. So what we can do is just to raise the bar. So for example, the amount of pixels that you need to change is going to be higher than before. The efforts that the attacker will have to make are going to be higher, or to make it near impossible in a real life scenario. But as far as I know, there is no perfect solution that will make an AI algorithm completely resilient to any adversarial attack. Now, still, the huge challenge is, what is the bar? What is an acceptable bar for adversarial attack robustness? It's in an open research question.
Yuval, in fact, from your answers, and also like if I check some of your earlier papers, there seem to be a lot of similarity between what you're doing in the domain of moving target defense, which was done over the year. Do you think like we can actually transfer the knowledge and like use what we have done over the years in that direction towards responsible AI future?
Yes, it's a very, very good question. Well, I think that one of the possible defense mechanisms, look, there are many types of adversarial attacks where it is very, very important for the attacker to know that with 100% is going to succeed. You're not going to go with a fake passport to an airport if you know that there is a 5% probability that you are going to be caught, even if you know how to forge a passport. Now, for such attacks, what we can do is exactly like you proposed, to use the moving target defense approach, meaning, for example, every model that we deploy locally is going to be induced from a slightly different data set. So in this case, the attacker will not know exactly what is the structure of the model on which data the model was trained. So for example, if you have a malware detection system in our computer, imagine yourself that each one of them is going to be trained on a different subsets of malware. Now, as an attacker, you are not sure what is the capabilities of the malware detectors. So if you want to be sure with 100% that the cyber attack will succeed, this moving target defense approach will discourage you from doing the attack because you are not sure that you will be able to bypass the AI system. Again, there is a very high probability you will be able to do it, but it's not 100%. And maybe in some cases it will be enough to discourage the attacker from launching the attack.
All right. Thanks, Yuval. That was a very interesting discussion, actually. So I would like to thank both you and David for presenting like this new direction and like all the efforts that are going into this. We do still have some questions in the Q&A, so please like have a look at them. But like to be on the clock, we'll be just switching to the next presentation in the meantime.
Okay.
So thanks again, and
thank you.
Thank you for inviting us. Thank you.